Hey guys, welcome to this page of the notes, and here's what we're going to do. I'm really excited about this one. Again, I mentioned earlier that when I first started teaching, actually some of the first classes I had were a chemistry and AP chemistry class, and so I love doing half-life problems because this is a direct application of chemistry and the decay of radioactive isotopes. So let's go ahead and do this problem. Here's what we've got. The half-life of a radioactive substance is the time it takes for half the atoms of the substance to disintegrate or to deteriorate to non-radioactive isotopes. All life on Earth contains carbon-14, which decays continuously, hint, hint as to which formula you're going to need, at a fixed rate. The half-life of carbon-14 is 5,760 years. That is, every 5,760 years, half the mass of the carbon-14 has decayed. Find the value of K for the decay of carbon-14. Well, this one's really easy. We've got decay, and I tell you, you need to find the value of K, so you need the formula Y equals AE to the minus KT, right? Again, decay, because I know it's decay, I tell you right in the problem, it's decay, and this one, continuous decay, because you're looking for the value of K. Now you may notice while reading the problem that it's interesting, I did not give you an initial or a final amount. That's because you don't need one. Think about it for a second. I tell you, right, the half-life of carbon-14 is 5,760 years. I then spell it out for you. I tell you what that means is that after 5,760 years, half the mass, half the original mass has decayed. So here's what you need to do. Pick any numbers you want to, right? As long as the original amount, the initial amount, and the final amount come out to be half of each other, right? You've got lots of options. I could make my original amount 100, my final amount would be 50. I could make my original amount 20, my final amount would be 10. If the original amount were 10, the final amount would be 5, right? As long as the final amount is half the original amount, you can pick any numbers you want to. Pick your favorite number, do half of it, and you're good. So, even though I didn't give you an initial and a final amount, I spell it out for you right here in the problem. You get to pick your own numbers. So here we go. I will do 50 and 100, because I like 100, it's easy. And then, of course, the time, 5,760 years. We're going to be solving for K. All right, divide the 100 to the other side, and you get 1/2. Surprise, surprise. Okay, there we go. Now, I need to solve for K. But the problem, again, just like the previous example problems we've done, the K, the variable I'm trying to solve for, is in the exponent position. I've got to get it out of the exponent position, and I can do that by taking a logarithm of both sides. However, instead of taking the common logarithm, I now have a base E exponential. Well, remember, the inverse of E is ln. And every calculator will have a natural logarithm button on it. It's that important. Every calculator is going to have one. So, in this case, instead of doing a common logarithm of both sides, I'll just take an ln of both sides. And I'm going to do ln because I have an E. And I know that E and ln are inverse functions. They cancel each other out. Watch this. ln of 1/2 is equal to the ln of E to the negative K times 5,760. Remember the way this works. Whenever the base of the logarithm and the base of the exponential are the same, they cancel each other out. So ln and E, see ya, they're gone, and I'm left with just my exponent. So I have the ln of 1/2 is equal to negative 5,760 K. Divide the negative 5,760 K to the other side, and I get K is equal to the ln of 1/2 divided by negative 5,760. k is going to be equal to, if you do this on your calculator, you should get 1.2 times 10 to the negative fourth, or 0.00012. This number won't have any units, it's just a constant, so you don't have to worry about units. Remember, it's a constant, it's the constant of growth, the constant representing the growth rate for this actually it's decay, sorry, it's the constant representing the rate of decay for this particular situation, and so we get a k of 0.0012, or scientific notation, which either way, it's the exact same number. All right, head on over to the next page of the notes and we'll take a look at another one of these problems. I'll see you there.